I'm again it.
I'm Sprite.
Hi. How are you?
I'm very well. How are you?
Good. Monday, which means that it's only 4 days to Friday.
That's true. So are we going to talk about our exam at all today?
We will next Monday.
Next Monday? Okay. Sounds good. Day for it.
I mean, study for it.
Yeah.
What questions do you have? I mean, I might talk about it a little, depends, but I wasn't planning on it.
Well, I'm just kind of curious what we should do to prepare the next specific.
Well, you have all those review sheets for each course,
Yeah.
each assessment. I have posted some stuff that says, you should look at these because there will definitely be problems about this last material there.
Well, I think also...
I mean, there will be a preponderance of problems about this.
Okay. Well, I think that one of the things that, there are like things that we did in each section that weren't on the review sheets necessarily. And so I guess the question is...
So then they're probably not going to be tested.
Okay. Got it. Thank you.
I mean, is my gut feeling.
Okay. Just making sure.
Yeah, and I looked at the exam. I have to redo it, but I looked at the exam this weekend, and I think it's fine.
Okay.
I mean, I don't think it has anything that will surprise you.
Okay. That's good.
Wow.
Oh, the Julius lash. What's wrong with you?
Oh my gosh.
Why are you doing that? Liz, oh my god. Are you good?
Raheem has joined the meeting. Hello, Raheem.
That just happened.
You're not at school.
You know, we only have 3 classes left until the exam.
That's true.
Not really.
Is that all you came for?
MIT early does have
Wait,
Saturday.
Wait, come back.
I didn't know that. You what? I didn't know that. You didn't get an email?
No.
Oh, you're sitting
I
there?
just apply early.
Everything okay in that other room? I can only see 3 people.
There's something definitely
So,
wrong.
Logan, Julius.
Oh.
Oh.
You're in here, huh? Why were you like trying to kill Isabel?
Trying to kill her?
Yeah.
Did you see everything that you see?
No.
Yeah.
So Izzy walked in and I went, boom. she had her stuff and she literally went like,
I thought she fell.
She went shook. So
And then like dropped everything and then I started laughing so hard.
Logan, I think you actually like killed this.
I didn't do it. It was Julius.
Can I watch it?
Well. That's all I can say.
Can we watch that video that just happened? Also, everyone look at my Santa mask.
There is no way it's not time to start class. Hi, Raheem. Do y'all have not have school today?
No, I'm still feeling well. Make your name and.
Oh, I'm sorry. I am sorry. Let's see. And who's that? I can't tell. Oh, that's Coleman. Hello, Coleman. How are you? Good to see you.
Hi, Mr. Spraggins. I'm not sure where
You're
Coleman
not
is.
Coleman
Did he
at all.
Tell you anything? No.
Huh?
Excuse me. I'm not sure where Coleman is today. Have you heard from him?
I have not.
Okay.
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 And let's see. Oh, okay. And there's Alex Powell. Hello, Alex Powell.
Hello.
How are you? Okay. And I guess where are the rest of your? Raheem isn't at Trinity Prep, and so things just go to pot. So they're not even here yet. And then we have an empty chair for Coleman. Coleman, you look very immobile today. Okay, let's do a problem to start. Here's something to get started with to just get us in the math mode. Let's see. I think I can do this problem.
Did the K in the denominator be uppercase or is it supposed to be?
What are you talking about? Nah. I see. It should be, yes. Yeah, so it should be capital K. There's Coleman, maybe. Yes, there is. we were just saying the empty chair scared us.
Yeah, could have been anything.
I know.
We had a run-in with one of your teachers.
Who, me?
No, Coleman.
Well, I wouldn't exactly qualify it as a run-in. That makes it sound like there were guns drawn or something. So that should be a K d del P over del K. Capital K. Hello.
Hello.
How are you?
Pretty good.
Where are the rest of your classmates? Trinity is having connection issues.
Yeah, I think there was like some construction going on, so they had to move to a different room.
Oh, hello.
Hello.
You look very pink today.
Yeah.
And Sam, you look very orange today.
Yes.
And it's like the whitest room I've ever seen in my life.
Yeah.
Is there a way you can turn?
Our other room.
Can you turn down the lights? And also your what is the word? Echo, 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 echo. Okay, Jasper, what did you get for del P del L? Best sound ever. Okay, Jasper.
Oh wait, I got L. Well, I got L times the quantity B K to the B.
Beta.
B K to the beta times. I think I have to do this.
It's alpha.
L. Alpha over. No wait. L over natural log of alpha.
Okay, so alpha I think is a so I assume that you would know this because I definitely, if I had been your teacher last year, I would have said almost always when we pick alphas, betas, things like that, we're talking about constants. So things from the beginning of the alphabet are typically constants. Things from the middle of the alphabet are typically what's the word? Like functions. Things from the end of the alphabet are typically functions too. So now knowing that, does that change your answer?
Yeah. Wait. So then I have just it's like x to the 3, and that's so since a over natural log of x.
No, x to the 3. How do you differentiate x to the?
I'm sorry.
Wow.
I'm sorry. Wait. Sorry. Oh. What am I saying? A L to the a minus 1.
There you go. Alpha L to the a alpha minus 1. Okay. I'm about to cry. Logan, help me feel better by doing the second term.
Sorry, I'm actually kind of confused about this one. You said it's
Yeah.
like alpha B times L to the alpha minus 1.
So for the first term, I have L times B times K to the beta times alpha times L to the alpha minus 1.
Wow, I missed a lot of them.
That
Okay,
actually
sorry.
multiply del P over del L by L.
Yeah.
Yeah.
Wait.
For my first term.
Can you? What's the BK part again? The beta.
Well, that's the part that's constant as far as L is concerned.
Oh, okay, yeah.
Okay? So, Logan, I'm waiting.
Sorry, so I'm still. Well, I missed the whole. You said you have L B times K to the beta.
Mm-hmm. And then times alpha L to the alpha minus 1.
Okay, and then why is it that we can treat, if L is a constant, then why is it that we can treat, because to me that seems like how you would differentiate like a polynomial like x squared.
How do you know L is
Yeah, it is. L is not a constant. It's the alpha that's the constant.
Yeah, that's what.
Oh, so that's where, okay, cool. So,
Yeah.
got that. And then right now you're
I
asking
made the same mistake, Logan. Sorry.
del P, del K.
Say it again?
Right now you're asking me for del P, del K.
Yeah, the second term.
So I would say that that's going to be, let's see. Oh, that's going to be beta times B L to the alpha times k to the beta minus 1.
That's right. And then all that times k. And then Isabel, does it work?
Well, I'm confused. Like, I did the math out, and sorry, not to be silly, but I just don't really understand. Like, once you get, like, AB times L to the A, K to the beta, plus, like, beta, B, K to whatever, equals A plus, or alpha plus beta times P, like, I don't, what do you, sorry.
Well, so I'm going to try to simplify the left-hand side, right? So I can simplify because I've got an L term, so I've got L times L to the alpha minus 1, so Alex Johnson, help her out.
So yeah, you have L times L to the alpha minus 1, and that simplifies to just L to the alpha. And then pretty much the same thing with K to the beta. You have K to the beta minus 1 times K, so that's just K to the beta. And then you add L del P del L plus K del P del K, and that gives you B K to the beta alpha L to the alpha plus B K to the beta beta L to the alpha, and then you can factor out B K to the beta L to the alpha, and then in parentheses you have alpha plus beta.
Yeah.
And B K to the beta L to the alpha is P, so then it's just P.
Yeah, so it does work. This Cobb-Douglas production function is probably the most famous multivariable function in the universe, actually. It's used in all sorts of industry, and I think there's a problem on the review problems about the Cobb-Douglas. I mean, it's really, 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 really famous, and it's used in lots and lots of industry. And so this is one of the reasons why I put it here. So that's something I promise you'll hear about the Cobb-Douglas production formula if you ever take a like an economics class that uses calculus, which you should take an economics class that uses calculus. Okay, so let's see. Today I asked you to approximate this Taylor polynomial for a certain function, and so for those of you who are not here on Thursday, here you need to make sure that you have this notes, because I think this is the only place that I've ever, I don't think it's in, I know it's not in any of the movies, and so make sure that you have these expressions, because they're expressions that you'll need to do this. And so the linear approximation has only the first partials with respect to x and the first partial with respect to y. The quadratic has the partials, you add on the terms that are the second partials with respect to x, second partial with respect to y, and the mixed partial, which is x sub y. And so for today, I asked you to do it for this particular equation, cosine 2x plus y plus 3 sine x plus y. And let me just show you my answer. So that's what I started with. So I have to do some calculations. I have to find what all these things are at 0, 0. Those are the numbers I got. And I am not positive that those numbers are correct, but I'm pretty sure they're right. And so then writing my linear approximation would just be 1 plus 3x plus 3y. Where's the 1 coming from, Samya? This first term? This term here? Samya? 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 I'm reaching out to you, Samya.
I'm sorry. That first, the 1 is coming from the f of 0, 0.
That's correct.
So that's coming from the cosine term, which
That's
is...
right. Okay. Excellent. Thank you. So that first term is coming from the f of 0, 0. Okay, and then I have, so that was my linear approximation. My quadratic approximation is my linear approximation plus these 3 other terms, and that's what I have for those 3 other terms. So check and see if you got that correct, and check and see if I got it correct. What do you think, Akshay? Did I do it right?
It seems like it, yeah.
Okay. I think that those are right. Okay, any questions about this? Notice that one of the things on the, Jasper, this one here, who's already freaking out about his exam, was like, what do I study for the exam? I had some problems up that are like obviously going to be important for the exam. The exam will have this recent material more heavily, like as a proportion of the actual exam, although it will be easier, I think, than the other problems from further back. So, but there will be like a significant portion of the exam will be about topics like this, but this would be a great exam question, something like this. Okay, are there any questions? You just have to know those two formulas. Okie dokie. So, I want to make sure we talk about differential. Yes, Giggles Gensler, how can I help you?
Is our exam on Tuesday? Like for
What?
the Meridian?
What?
Is our exam on Tuesday for the Meridian?
Yes.
That's what I just make sure.
Okay. So this is a differentiability. Would you read this for us, Eric?
Sure. Theorem. Suppose the function f has partial derivatives f of x and f of y, defined on an open region containing a to b, or ab, I guess, with f of x and fy continuous at ab. Then f is differentiable at ab.
So how is that, Eric, similar to like differentiability in the world of single variable calculus? What has to be true about differentiability?
That it has to be continuous.
And there has to be
at the point.
A derivative, right, at the point. So it's very similar. The only difference is here you have to have a derivative with respect to x and a derivative with respect to y for it to be differentiable at a point in three-dimensional space. Okay, Raheem, could you read the second theorem?
If a function f is differential at a to b, then it is continuous at a to b.
Yeah, and that's the same as in single variable calculus, right? So differentiability implies continuity. Do you remember that idea? Differentiability implies continuity. Now, does continuity imply differentiability, Raheem?
Not necessarily.
Yeah. So can you give me an example of something that's continuous but not differentiable?
Okay.
There's a classic example.
Of a specific function.
Yeah.
I can't
Someone
think of
know?
Go ahead.
Samya, do you know? I have no idea
Wait,
if
did you
Samya's
say
saying anything.
Oh, yeah,
Do
yeah.
you have yeah.
The absolute value function.
Yeah, the absolute value of x is sort of the classic example because at the point it is non-differentiable because it's changing too rapidly. So that's a classic example. So this is exactly the same. Differentiability in 3 dimensions implies continuity, but continuity does not imply differentiability. Okay, that's just to make sure that you all know those definitions. So they're very similar to in single variable calculus. Now today I want to talk about the chain rule, which in 3 dimensions is somehow more complex than it is in 1 dimension. So the chain rule is a funny thing. So let's see. So you've got a function here where you've got z is equal to xt squared y plus 3xy to the fourth, and those functions are also functions of t. So x is a function of t and y is a function of t. And we might want to find dz dt when t equals 0. I have no idea how to start. Sam, can you help me think about this problem?
Oh.
No.
Okay. I have the microphone on.
Okay, so Alex Powell, can you help me?
So first I want to so first find the partial derivative. So I want to find dz dx, or no. I want to find dx dt and dy dt first.
Okay, so let's find dx dt and dy dt first. Okay, so Sam, can you find del x dt? Can you find that dx dt, rather, I should say. Sam, you can do that. I know you can.
Okay. Can you mute that?
Now we're supposed to
All
hear
right,
what he's
that's
saying.
better. Okay, so dx dt is 2 cosine 2t and dy dt is negative sine t.
So dx dt, I think, is 2 cosine 2t, isn't it?
That's what I said.
Okay, I couldn't hear you. There's some problems. Coleman, can you find dy dt?
It is. It's negative sine t, correct?
That is true. That is true. Okay. Let's see. Max Allen. Now what do I do?
Yeah.
Max, what do I do next?
So, dz dt is del. I'm pretty sure is del z del x times dx dt, right? So we need to find.
So that's the idea. That's the strategy always. So let's take the function's derivative with respect to one of the variables. So let's do that with del d del x. So Max, can you do that for me?
Yeah. So del z del x would be 2xy plus 3y to the fourth.
Plus 3y to the fourth. That is correct. I did it wrong on my paper, Max, but you're smarter than I am. Okay. Julius, now what?
We just did del z del x. So we need del z del y.
So we also need del z del y. So Julius, go for that.
X squared plus 12xy.
X squared plus 12xy cubed. Okay. Okay, and Charles, how do we put it all together to get dz dt?
So you use the formula that dz dt equals del z dx times dx dt plus del z del y times dy dt.
Okay. Now I have a problem, which is that I have things in terms of x and things in terms of t. So the derivative, the idea is that I'm going to take del z del x, multiply it by dx dt, plus del z del y times del y dy dt. So I'm sort of fumbling there because it's funny notation. But what I'm thinking about is I'm taking the derivative of the whole function with respect to x and y, and then I'm multiplying those by the derivative of the we have a name for them. I don't remember. We'll see in a second. It's not intermediate function. I don't know. Anyway, we'll see in a second. The functions that are the composite functions that you're composing, you multiply by the derivative of those. But I get, Charles, so let me read this to you, Charles. I have 2xy plus 3y to the fourth times 2 cosine 2t minus sine t times quantity x squared plus 12xy cubed. That doesn't look good.
No.
So what can I do?
So what you can do is you can evaluate the dx. So you can evaluate dx dt and dy dt at the point that's given and get a number, and then plug that into the chain rule function, and that gives you.
Okay. What if I wanted it symbolically? I mean, I wouldn't want to have x's, y's, and t's. So what could I do?
Then you'd have to plug in the equations for x in terms of t and y in terms of t.
Right. I would write, instead of writing 2xy, I would write 2 sine 2t cosine t.
Could you just do the other? Oh.
Yeah, but they're much uglier, so you would probably want to put it in terms of t. Okay, so let's actually do because we're computing this at t equals 0. So Jack, can you help me compute del x dt at t equals 0?
So del x dt is going to be 2 cosine t, which at 0 cosine of t is 1, so it's just 2.
It's 2, so dx dt is 2. Okay, Jasper, what is dy dt at 0?
dy dt is going to be 0.
Psych, so that we don't even have to worry about that second term. We also need to know x of t at 0. So what is that, Logan?
X of t at 0 is sine the 0.
Okay, so that's awesome. So Samya, what's y of t at 0?
Y 0 is going to be 1.
Yeah, so I think that all I need to do then is I have 3 times 1 to the fourth times 2. So that's, let's see, I think that's 6. I hope we'll see. Okay, so I got 6 for this answer. So evaluating it at a point, you're going to get a number out. What does that mean that I got 6 there, Alex Johnson? What is the 6 telling me?
It's just like the partial derivative of z in terms of x at t equals 0.
So what is it telling me about z? As t increases, what happens to z?
It increases by a factor of 6.
It increases. Okay, not by a factor of 6. Be careful, because I don't really know that. I guess that's one way to think about it, but because you could actually write z as a function all of t.
Yeah.
So its slope as a single variable function is 6 there. Okay, so it's increasing at that point. Okay, so let's try a different one of these. So let's do this one. So let's do this one 2 ways. So here's z prime of t. Z is equal 1 over x plus 1 over y. So you should be able to do this unguided by my able hands. You should all be able to do this by now. And there are 2 different ways. So let's see. I want Akshay, Eric, Rahim, Isabel, and Sam to do A. And I want Coleman, Alex, Jack, Max, Julius, and Charles to do B. And then I want the other 4 students to do, just pick A or B. I don't care what you do. Alex Powell, I want to do.
Yeah.
Okay. We have such terrible feedback coming from you, Samya.
Oh, sorry.
I think if you turn down your microphone or mute, that will work. Let's see. I think I'm going to use the chain rule.
What's so funny?
I have a question.
Yeah.
So when we do the chain rule, when you just ask us to do the derivative, do you want us to replace x and y?
Yeah, you want to get it all in one variable because that just looks wrong.
Okay, got it.
And also, the information you care about if you're looking at z prime of t is how it's changing with t. So yeah, that's a great question. But okay.
I feel like. Oh, never mind.
So you should have, I hope you've gotten A or B done. So let's hear a representative of the A group. Isabel, what was your derivative? Really? Isabel?
Sorry. I was just talking to myself. Okay, so I got that z prime of t equals negative, and then in parentheses t squared plus 2t to the negative second, and then that times 2t plus 2, and then plus negative 3t squared divided by parentheses t cubed minus 2 all raised to the second power.
Okay, cool. Akshay, did you get the same thing?
Can you repeat the first term? I got the same as the second.
2t, negative, then parentheses 2t plus 2 divided by parentheses t squared plus 2t all raised to the second.
Yeah, I got that.
Okay, cool. Okay, so Alex Powell, let's hear how you did B.
So I got.
Can you explain how you did B?
Oh, explain how I did. Okay, so first I found dx dt and dy dt.
And so what did you get for those?
dx dt I got 2t plus 2, and dy dt I got 3t squared.
Excellent. Okay, and then what'd you do?
And then I found dz dx, or del z del x and del z del y.
And what'd you get for those?
I got negative 1 over x squared for del z del x and negative 1 over y squared for del z del y.
Me too. And then Julius, what did you do?
I put them, dz dt equals del z del x times dx dt plus del z del y times dy dt.
Excellent. And then you're just plugging in expressions. And then your last step is to put it all in one variable.
Yes.
Okay. And you get exactly what Isabel and Akshay got earlier. I did it myself to prove it. Okay, so the chain rule, while it seems really intense, like when you look at like an expression for the chain rule, it's really not that bad. Let's just do one more, just because this one is a little more complex, because the other here I've got these functions. My other functions are multivariable functions, so I can only find things like del z del s and del z dt. So I'm wondering how to start this problem, Eric. What do you think?
So I think you would take a very similar approach to the way we did the other ones.
Okay. So tell me how to do it. I'm really bad at this.
You would take del z del x. So partial derivative in terms of x, del z del y, and then dx dt. I'm sorry, so we're finding both dx. So yeah. So. Then dx dt and dx dt, dy dt, and then that would give you the necessary parts to solve for dz dt.
Okay, so it's like, this is how we like that why we like that Leibniz notation in a way. So when I'm writing del z del s, I wrote del z del s equals del z del x times del x ds, as in Spraggins, okay? Plus del z del y times del y ds. Because what I'm trying to do is I'm trying to see how the s is affecting the x variable plus how the s is affecting the y variable. So let's see if we can compute that. So Rahim, can you do that for us and walk us through what you're doing?
Yeah. Okay, so first you want to find the del x del s and the del y del s. So then del x del s, you would get t squared. And then for del y del s, you will get 2st.
True.
And then you want to find del z del x and del t del y, or del z del y. And then for del z del x, you will get sine y e to the x.
Yep.
And then for del z del y, you will get e to the x cosine y.
Excellent. And then your final kind of effort is to put everything, I would put everything in terms of s and t. Okay? So I would have e to the st squared sine of s squared t times quantity t squared. You get the idea. Okay? Rahim, thank you. Coleman, can you do del z del t?
Yeah, so you'd want to get del z del t would be equal to del z del x times dx dt plus
now be a little careful. Sorry, Coleman. Be a little careful because it's actually del x del t, right? Because it's a multivariable function. So that's the difference between dx. We only use that when we're talking about single variable functions, but the del, it's a subtlety, but I want you to speak like a mathematician. So go ahead.
Okay. Plus del z del y plus times del y dt.
Excellent. And can you tell me what those things are?
Yes. dx dt is 2st, and dy dt is just s squared.
Great. And you already know from above what the del z del x are. So again, your final step is your expression will be a multivariable expression in s and t. Okay. So try not to have, that's 4 variables. It's just too many. Okay, thank you all. This is good. I always think this is so hard, and then I just am wrong because it's not typed. Yeah, Julius.
Did you write that out?
Could I write it out?
Like, did you?
Yeah, I did.
Is there any way I could see that? Just because I can't
Sure. I stopped writing after a second because I got bored. I have to continue to write it out. Jeez, Julius, you're so demanding.
I'm looking at Alex's, it's fine. Wait,
okay, there's my expression. You can pass that to Julius. Okay, notice there are these three types of variables here. Here's what I was trying to remember. So the independent variables are the s and the t. They're the ones that are the most embedded in the function. The intermediate variables are x and y, and then the dependent variable is a z. So just to make clear that what those functions are. Isabel, do you have a question, or do you have was this a relic of something else? Okay, so there's independent, intermediate, and dependent. So we often see these charts that you will encounter in any kind of multivariable book you see. So can someone explain what's going on in this little chart down here? I'm wondering if Jack can help me with this chart. What's happening? This is such a common thing. Every multiple variable calculus textbook in the world uses the same kind of chart. What's it trying to tell me to do?
Well, it's effectively just like, it looks just like a visual of what you were just describing. You have the derivatives with respect to the intermediate variables of
excellent.
Of z, and then like taking the next step after that, you have then the partial derivatives of the independent variables within the intermediate.
Yeah, great. And then Max, if I wanted to find like dz dt, what would I do?
Dz dt would be
or del z del t, I should say.
Okay. Del z del t, you would just take del z del x and then multiply that by del x del t.
Okay, and then you'd add.
And then you'd add del z del y plus or times del y del t.
You see what these charts are helpful because they're kind of like tree charts and probability. They're trying to help you make sure that you've accounted for all the possibilities of having the derivatives. So they can be rather complex, like if you have multiple things. So, like here, this is a general version of the chain rule. Let's say you have this many variables. You have x sub n variables, and each one is differentiable. And then, so your chain rule is always going to be, if you wanted to find the partial with respect to the first variable, you would take the partial of the whole thing with respect to x times the partial of x1 with it's not terrible stuff. It just looks scary. Yeah, Julius, can I ask you answer a question for you?
So the way that you do you'll be like del z del x times del x del t to get del z, and then you have to add the y side. But when you I feel like if you cross out your del x's and you're left with del z del t, then you shouldn't need the y term to make it complete. You do.
Well, you don't. Right. For here, this is asking del u del t, and this has the variables are just x's, a bunch of different x's. So you can think about this as this x1. It's a little abstract to say this, but x sub 1 could be x, and x sub 2 could be y, and x sub 3 could be z, and x. So what this is doing, though, is each piece of this is accounting for how the function is changing with respect to that variable, and how that variable is changing with respect to the variable of interest. And so you're just adding up a whole bunch of terms that is telling you that. So it's actually, in a way, I like the chain rule in multivariable calculus. It really looks like a chain, whereas the chain rule in single variable calculus doesn't really look much like a chain. But you have a chain of terms. Each one is telling you how the whole function is changing with respect to that variable.
One term.
Yeah.
So I feel like in the this is just really specific, but I feel like in the way that you note it, you should have some sort of tie back to x. It does here.
So do what?
No.
Well, actually, if you think about this, this is the first two terms is the way that you learned the chain rule before, right? It's saying you take the derivative, if your interior function is a Actually, I should stop saying that because I don't think that's true when I look at it. Okay, so let's write out the chain rule for the case. So here I've got, this is really the worst kind of possible scenario. You have 4 variables, okay? Your variables are, that's your intermediate variables are also variables of 2 variables. Oh my gosh, I love it. So you want to write out the whole, like if I wanted to find del W del X, what would that look like? I mean, they all would look alike, so just write out for one of them. I'm sorry, I should say del W del U, sorry. Isabel, you have a question?
No, I just raised it to answer.
Oh my goodness, okay. Did you make a tree, Isabel? I'm curious.
No. Sorry.
Fine.
I'm sorry, I didn't.
I'm going to make one.
Oh, that sounds good.
Thank you. Like I need your approval.
I'm sorry, what, Max?
I don't think what I did is right.
I have faith in you, Julius.
I don't do. What are we doing? Del W del U?
Wow, that was a little
I
harsh.
think nobody asked you.
Yeah. It just takes a long time to write out.
I don't think this is that bad, though. It's just a
Okay. Charles Dawson, do you have an answer?
I do.
Okay.
My answer is del W del U equals del W del X times del X del U plus del W del Y times del Y del U plus del W del Z times del Z del U plus del W del T times del T del U.
Yes, I like that. You know, hey, Charles, can you make a conjecture? If you have 4 intermediate variables, how many terms will you have?
4?
Yeah, I mean, I think that's how it will work. So let's see. I think I even have a picture of yes, here is the chart. I drew this same chart. So why this is allegedly helpful, like del W del U would be following things down the red paths here, and del W del V would be following things down the blue paths. So, you know, this is one of those things these charts may or may not be helpful to you. It's kind of like an accounting thing. It's really just making sure that you know that you've got all the terms. Okay? Make sense? Sound good? Okay, let's talk about. Oh, let's not do that. Okay, and let's not do that either. Okay.
Mr. Dragon.
I want. Yes. Sorry.
I have a
Max.
question.
Yeah.
So, in this case, it's a little different, but for the function, not the function we just did, but the function before, where you have W or Z equals a function of X and Y, and then X and Y are a function of T, right? So technically, if you compiled everything, it would just be a single variable function, right?
Yeah.
So why would you ever see it not as a single variable function? Like what?
Like, why would someone do that? Are you talking about this problem, Max? Look on the board.
Or even the one before that, I think.
I think it's the same function.
Okay.
So the question is, why would you want that? Okay, so Isabel has a suggestion.
Well, like a lot of things are like functions of other things, but let's say you wanted to know like wind speed as a function of temperature and pressure, and then like temperature and pressure are both functions of other things. So like it's easier to just look at like, okay, like the wind is this when temperature and pressure are that, but if we want to base it off of like altitude or time of day, then you like delve deeper.
Right. So Logan, you have an idea too?
I actually have a question.
Okay.
Is this how I know nothing about statistics, but is this how like when they're looking for correlation and causation and stuff, is this how it works?
Oh, I don't think so. I don't think it's related. I mean, how do you think that? I mean, are you thinking of the tree things? Are you thinking of the tree things?
No, I'm just thinking of like when you're looking at like a statistical study and you're trying to like isolate one variable out of many, and like this seems like a similar way to, I don't know, but I guess not.
Well, so, I mean, one of the things I'll say to you is that there's not a lot of calculus in the world of statistics, actually. There is some, okay, and there's certainly probability used calculus used in probability problems, but in the world of statistics, it is mostly algebraic, so the normal curve is defined as an integral, but, I don't know of any, Logan, but I could be really, really wrong. So I'll ask my colleagues and see if I know anything. But I don't think it's been used in statistics much. So Max, I think the short answer is that sometimes the thing you can control, like in this example, maybe the only control you have is over the st squared. For Isabella's example, like let's say you were interested in wind speed, but you could somehow control, temperature. I don't know. You're working in a laboratory setting where you have a big wind tunnel and you can change the temperature, you can change the pressure. So, I mean, that might be the way that these things work. It's just like any function that's input, the independent variables, that's what you care about for whatever reason. A lot of these, and I always laugh about them because certainly when I teach differentiation, and like we just looked at something today that was very useful, but we often see things that are basically intellectual exercises, and some of these things will have to be that way. They may not be obviously apparent what they are. So implicit differentiation, we learned back in the day, right, in one of the first things you learned in calculus, and there turns out that there's a formula for implicit differentiation using partial derivatives. And Jasper, could you explain the formula?
Well, so it comes from, if you like separate it out, you'd have dy times fy, and then plus dx times the partial derivative with respect to x. And then
so that's why we usually talk about when we talk about the chain rule, but it's a simplified formula. So what is the dy dx is equal to the negative of the partial with respect to x over the partial with respect to y. So, again, you may be doubters, okay? So, Jack, can you help me do this the old-style way, how we learned to do it last year?
Yeah, so it would be 2x minus 4y times dy dx.
I agree. And then what do? You isolate the dy dx.
Yeah, get rid of it.
And so I get x over 2y equals dy dx. Okay, so let's try to use this handy-dandy formula, negative f sub x over f sub y. Okay, so Alex Johnson, can you help me use it? So what's f sub x?
Partial derivative with respect to x, so 2x minus, or just 2x.
And then the partial with respect to y
is negative 4y.
Yeah, and then it's not the same because remember we have a minus sign in front, so it is the same. So it's just a much more convenient way to implicitly differentiate, which, if you remember, I hope your math teacher taught you implicit differentiation as a result of the single variable chain rule. That's really what's going on with implicit differentiation. So that's why we generally talk about this. Okay, so now let's play one of our favorite games. Are these things true or false? Okay, let's see how we do. I don't know. Okay, Charles, you're up first. Is that truthy or falsish?
What? I say that's true.
Okay, so you say it's true. What is the function you're thinking of?
F of x, y, f equals xy, x times
so
y.
X, Y. Okay, so let's see. Logan, do you agree or disagree?
Sorry, I'm playing catch up right now, so I didn't really hear that.
Okay, Samya, agree or disagree? He says it's true.
Agree.
Okay, yeah, I mean, that's why would work, wouldn't it? Okay, there we go. Good. Okay, Akshay, truthy or falsish? Oh my gosh. So we have to actually do some computations here. I have to do some computations, Akshay, because I'm just not on top of it yet. So.
I'm kind of lost here.
So do you understand? So I'm just saying, does it satisfy that equation?
All right, so we should take the do the chain rule.
Well, we don't actually need to here because we've just got a good old average multivariable function. Right, u is not a function of some other variable, and nor is v. So actually, I'm just trying to see if it satisfies this equation. So I need to compute what del z del u is. What is that, Akshay?
Del z del u is negative u sine v.
Del z del u. So u. I don't think I agree with you. I hate to say that because I, of course, respect and admire you. Eric, what do you think del z del u is?
I got cosine v.
Yeah, I think it's cosine v. So Akshay, del z del u, as far as u is concerned, cosine v is just some number. It's like 12.
Yeah.
So it's like 12u. So the derivative would be just that part. Okay. So what would del z del u be, Akshay?
Del z del u would be
same thing.
Oh yeah, the same thing.
Okay, so I got cosine squared v minus sine u cosine v over u, and I don't think that's equal to 1. So I would say that's falsish. Okay, here we go. Alex Powell. Ooh, my gosh, what on earth is going on here? So you've got a function of two variables, and g of x is a function of a single variable. Then the partial derivative with respect to y of that would equal, so just g of x times the partial derivative of the second with respect to y. What do you think, Alex Powell?
I would say that that's true.
Is it true or is it truthy?
Or truthy.
Okay, so why do you think it's true?
Because if you take the derivative with respect to y, then g of x won't change. And then f of x, y, it would just be the partial derivative with respect to y.
Okay, let's see. Raheem, what do you think?
Well, because the way I'm thinking about it is, yes, that is true with respect to the g of x, but then the partial derivative with respect to y of f, I don't think would be the same as the original function.
Oh, it's not. Look closely at the slide. So it's got this thing, ding, this right here. Right?
You can just cross out gx.
Well, because gx is basically a constant.
Yeah, so since g of x is some constant, so I think that Alex Powell is correct, is that in fact that is right. That is true.
Wait,
yes, Isabel?
couldn't you just like, isn't g of x, okay, it's a constant, so cross that out from both sides, and then you get del, you get the derivative with respect to, never mind, sorry.
Right. It's just different notation. I mean, that's one of the things that's confusing about it. But also, since this is independent of y, I mean, you could pull it out in front and then just take del y of f, which this is another way of writing that. Yeah, Alex Johnson?
The parentheses.
Just that was my question. Like, to clarify, so like the del over del y applies to what, like,
it should go to everything.
Even if like the whole.
Maybe this parentheses here is troubling to people.
A little bit.
So sorry. And all I can say is let's move past it. Let's move past it. Yes, Julius.
So on this side, the del thingy, on the left side of the del y thing is
times the whole left side.
The whole thing.
Yes.
And then on the other side, the del y isn't.
Well, because G, this thing is not dependent on y. So it's just like some number as far as y is concerned.
Yes.
That's maybe why this is truthy, because this thing here is problematic. So that's why it's only truthy, not true. Okay. The function k of rs equals rs e to the s is increasing in the s direction at the point rs equals -1, 2. Oh my gosh, we have to do another calculation here. So what am I looking for here, Coleman? What am I thinking about? I'm thinking about del k del. Coleman.
Del k del s.
Yeah, that's what I'm thinking about. That's what I'm wondering about. Okay, just to make clear, so we don't spin our wheels on that. So let's see. Ooh. Okay, so I computed del k del s. Samuel, did you compute it? And what did you get?
I'm in the process of doing it, so I got r times the quantity. R s times e to the s plus r times e to the s.
I agree with you. Okay, good. So then, Coleman, what would I do next?
There's a hand.
You would find I'm not sure.
Oh, so I'm given a point. So now I just plug in the numbers, okay, for r and s. So -1 is r and s is 2. So let's see, I'm going to put in, so I have 2e to the -1 minus 2e to the -1. And then I have to decide whether that's positive or negative, which I think it's 0. Did I make a mistake?
Well, I think r.
Oh my gosh, it's r e to the s. Ooh, I did it backwards. Bad.
R e to the s plus
it's
r.
It's e squared minus 2e squared. And that's -3e squared, which is negative. So what can I conclude, Coleman?
Oh my god.
That it is false-ish.
That is false-ish, right? Because it's not increasing at all. It's decreasing, in fact.
It's e squared minus 2e squared?
It's negative e squared minus 2e squared.
I mean, regardless, it's negative.
Okay, it's neg. Okay, and I think here's another one. We still have one more. Truthy or false-ish? I think it's Max's turn. Maybe not.
Ooh, that's fine.
Max?
Hold on. Hold on a second. Okay.
No, I cannot hold on.
I think. Wait, hold on. I think this is false-ish.
I think it's false just too. I don't think there is one that works for this. So we let's just do this one last one. We have the last. So Jack, you're going to finish this out for the day. If f of x has the derivative with respect to y is 0, then f must be a constant.
I think that's false-ish.
Okay, can you give me an example?
F of x and y equals x squared.
Yeah, x squared.
Yeah.
Now, the real question is that a function of x, y? You know, and so that's why I think this one's a more interesting question to ponder. Jasper, you had a...
Go back to the one before.
Oh, he wants to go back, so he's not convinced, Max.
Because what if we have y cubed over 3 plus x cubed?
Y cubed over 3 plus x cubed over 3. Well, the derivative with respect to x would not be y squared.
I thought it was with respect to y. Yeah. Well, sorry.
Shucks.
Right.
Okay, let me talk a little about. So we're done with the chain rule today. So that's often a very intimidating idea. We're going to talk about the gradient, which is a very easy idea, on Thursday. And then on Monday, I'm going to talk about the exam, and then you're going to take the exam, and it's going to be so much fun. And I'm trying to engineer something for you all for that exam, so we'll see if it happens. Have a lovely day. You have something to do this week.
Mr.
Spraggins.
Mr. Spraggins, I have a question about the exam.
Yeah.
So on the website it says that.
What does he mean by engineer?
On the website it says that we have to take it by 12 p.m. on Friday.
No. So what I have to have it done, not this Friday. It's the wrong date if it says that.
It says next Friday.
Okay, so when are you out for a break?
Well, we were going to take it at 12. Like, we have it scheduled from 12
to 1.
That's okay.
That's fine. I just have to get it that day. Here's the reason. Because I have to turn my grades in, like, the next day.
Okay.
Really? Okay?
Okay, yeah. Because we're taking it next Friday. So.
And Coleman, is that okay? You're going to be able to take it next week sometime?
Yeah, I should be taking it Wednesday or Thursday.
Okay, great. And Alex Powell, how about you?
How long is it supposed to take? How long is it supposed to take?
How long do you have to take it?
Yeah.
Oh, so it is written to be like a 2-hour exam, but you may have up to 3 hours to work on it.
Okay, then I'll have it done sometime next week.
That's what you said last year.
Well, I didn't mean it last year, but this year I really do. So Alex, so it's like a 2 to 3 hour window you should arrange. Okay?
Last year?
Okay, bye. See you.
Okay, bye.
And then he's going to engineer
Bye,
something. Oh.
But we're definitely taking it on Tuesday.
Yeah, there is definitely no negation.
Why am I so tired?
I just don't understand how we're only going to talk about it on Monday.
Yeah, one day of
That sucks for us.
Like, obviously, we have the weekend to, like, study and stuff, but if he never covers these
If we don't know what we're supposed to
topics,
study over the weekend of studying.
That doesn't make sense. So we can't take it like Thursday? We have to take it on Tuesday.
yeah, that's why I asked.
Take it whenever.
Because
Because we can?
I don't know.
no,
we'll
I
probably
really
have to
don't
take
think
it
so. I think he's
well, I
like
guess
offended by the idea of changing the date.
Yeah, I think he
We should
This class is just like
This exam is gonna be awesome.
this
Like,
whole
even
MSON
if he,
system is just.
can you please say that to the administration? 'Cause-
I'm waiting for the next like MSON review questionnaire thing.
No,
and
but
it's gonna
can
be
you
like,
just say it? Because, like, I've said it a million times, and so has Alex, and so has a bunch of other people. Like, it's not a horrible idea, but it's just not fair to the students.
Yeah, we should definitely should.
It's not funny.
Julius has watched it 3 times.
You guys were talking in the all chat.
Yeah, I know, we noticed. Hey.
Wait, let me see. Come on.
Like it's funny in the video, but in person it was no funny.
I've never been in this room. Never been in this. I've been in like 4, but now it's like 5.
Yeah.